So today we're looking at the problem remove k digits. The description of this problem is very simple. We're given a string num representing a non-negative integer num. We're also given an integer k. So we want to return the smallest possible integer after removing k digits from num. Notice this says removing k. This is not at most k. This is exactly k digits we have to remove. So we see an example here of a 1, 4, 3, 2, 2, 1, 9. We can remove the digits 4, 3, and 2, which will give us 1, 2, 1, 9. And this is the smallest number that we can make by removing 3 digits. So let's think about how we actually get to this logic. So let's say we're starting with 1, in this case the first element of this number, and then 4 comes along. So say you remove this 1 in place of the 4. What would happen next? So we'd either have 1 or 4 as our base numbers, right? So say a 2 comes along next. So in this case, we would get 12 versus 42. So from this, we can kind of see that our leftmost number is the most important in making a number smaller, right? If this was, say, instead of 5, this would be automatically larger no matter what comes after this. So the idea here is to kind of prioritize having our smaller numbers as far left as possible. And we can do this by using a stack data structure. Stacks are kind of great for looking back at elements that you've already seen and maybe like making a decision about whether to remove them or keep them. So essentially what we want to do here is have a monotonically increasing stack. And what that means is that the values in our stack will always either be increasing or equal to any values before it. So let's see what this actually looks like. So let's say we're at 1. So we add 1 onto our stack because there's nothing there. And now our k was originally 3 and it's still 3 because we haven't moved anything yet. So now we add 4. We see, is 4 less than any elements that came before it? It's not, so we just add it onto the stack. So now we move on to 3. And we ask the same thing. Is 3 smaller than any elements that have come before it? Well, yes, we see that 3 is smaller than this 4. And we know that if we replace the 4 with the 3, any elements that come later, it will automatically be smaller. Because look at this example. We could have 1, 3 or 1, 4. If a 5 comes, we'd end up with 1, 3, 5. Here we'd end up with 1, 4, 5. So we're replacing this 4 with a smaller number. We're always prioritizing smaller numbers as far to the left in our final number as possible. So we remove this 4 in favor of the 3. But at this point, we removed an element, so we have to decrement our k value. Then move on to 2. Same thing here. This 2 is smaller than 3. So again, we remove this 3 and add the 2 here. Again, decrementing. So now we have 1 value left to remove. So now we move on to 2, this next 2. It's not smaller than elements that come before it, so we're going to add this here. Then we move on to 1. So what we're going to do is say, okay, so 1 is smaller than this 2, so we're going to remove this 2, and then our k becomes 0. So at this point, we have to stop, right? If we had a limited amount of numbers that we could remove this 2, but unfortunately, we've already used up our allotted number of elements. We have 0 left we can remove. So we're basically forced at this point to use this 1. So now we add 1 onto the stack, we move on to 9, and we add 9. It doesn't meet our condition of being less than any of the numbers before it, and even if it did, we can't remove anymore, so we're kind of just stuck with whatever comes next. So you'll see here we have 1, 2, 1, 9. So if we join that at the end, we get 1, 2, 1, 9, which is exactly the same as was provided in the solution. Another interesting example is this 1, 0, 2, 0, 0, and we can remove one element. So the final answer here is actually 200. So this might be confusing because our original number was 5 and this is 3. So clearly, even though we have k equals 1, 2 elements were removed. So what ended up actually happening is that we removed this 1 and this ended up becoming 0, 2, 0, 0. So even though this is a string, it follows the rules of regular numbers and we cannot have a leading 0. So this kind of gets removed by default. So this is another thing that we want to keep in mind. If we have trailing zeros, those are something we have to remove. There's a couple ways to do this. We could kind of just treat the zeros as regular characters in our stack. So we can just like add the zeros in if we have them, continue from there. In this example, we'd end up with 0, 2, 0, 0. And then with our final result, we would just look for any trailing zeros and just remove them. We could also take the approach of if our stack is empty and we see a 0, we just don't add it in and we don't count it towards our k value because this is just an illegal element basically. We can't have this as part of our number if it's the first element in the number, so we just don't consider it and we move on. And I'll show you exactly how this works in the code. So this example uses the approach of not really considering the zeros as part of a valid number if they are leading zeros. And I'll show you how we do that. So first we just get n, which is the length of our number, and we create an empty stack. Then we set toRemove, a variable which is equal to k, and we're going to decrement this as we remove elements. And when this hits 0, we basically know that we can't decrement anymore. We just have to use whatever elements that we get. So then we iterate through each character in the number. So if our stack is empty, what we want to do is check if the current character is 0. And this is the case I was talking about where we don't want to include trailing zeros, or rather leading zeros, as part of our number. So we just continue past it, but notice that we don't decrement our toRemove value. And this is because technically a leading 0 is not a valid character that we can have in this case, so don't even consider that we removed it. It just kind of by default gets removed as part of it being an integer. Otherwise, we just append whatever character this is onto our stack. Then what we're going to do is while our stack is not empty and while our current character is less than whatever is at the top of the stack and we're still able to remove elements, we're just going to pop that element off and decrement our toRemove by 1. So then this is kind of a continuation of that 0 logic. So basically we're going to see if our stack is empty and our character equals 0, we just continue. Otherwise, we're going to append that character. So then at the end, it's very possible that we didn't remove all the k elements. Certain orderings, this would happen. And what we want to do with this case is just kind of remove whatever elements from the right side of the number that we have left. And we're moving from the right side of the number because, as we discussed, elements on the left side contribute the most to the element's value. So if we have a 1 in the first spot as opposed to a 9, that can change the value to much greater capacity than numbers coming after that. So basically I just want to, while we have elements we can remove, we just remove them from the stack. and decrement. Then what we do is say, if there are elements in our stack, we just join those into a string. Otherwise, we return 0. So let's submit this and make sure it works. And it does work and is accepted. So thank you for watching. I hope this was helpful.